share his treasure with anyone? Because he's a little shellfish. All right, well, let's just do some math then. All right, so folks, chapter 4 is about solving systems of inequalities with matrices. So let's just clarify this idea one more time, okay? What we did in chapter 3 was solved problems using a graphical method. So I'm just going to throw up here a simple example. I'm not going to throw up. I'm going to put up an example. There we go. Here was an example right here. You don't have to write this down. It is in your packet already. In fact, just go ahead and turn to this problem. Turn to page 3. I'm sorry, number 3. Go to number 3. And let's just kind of jot this one down a little bit together. Is everyone? Number 3? Oh, it's right there on the first page. Well, there you go. So what we're saying is we want to maximize this objective function, 2x1 plus 8x2. And we need it to be subject to these two inequalities. And we're only looking at positive values, right? So let's just real quickly make a tiny little graph. And I'm just going to solve those inequalities for x2 in my head here real quick. So y is less than or equal to negative 1/7 x plus 15/7. That's one inequality. And then y is less than or equal to negative 7/3 x plus 25/3. That's the other inequality. And so 15/7 is really 2.14, and 25/3 is really 8.3. Okay, so this is what our graph would look like. You'd have a y-intercept at 8-ish, and that would be down 7, right 3. So that graph would look like this. You have another y-intercept at 2, but that slope is very down 1, right 7. So that would look like this. There we go. And so they're both being shaded down, and so this would be your feasible region. Okay, I'm just kind of walking us through how we would have solved this problem last week. So we've got our feasible region here, and then we would note each of those corner points. We would have to find each of those corner points. We don't necessarily know those corner points right off the top of our head right now, but there would be values for those corner points, and we would plug each of those corner points into the objective function, kind of like in a table like this. We would say, hey, the objective function is 2x plus 8y. We'd plug each of those corner points in and then see which one of them was actually the max. Okay, so does that sound right? Does that sound like what we did last week?
Yeah.
Okay. So this week, we don't want to do this whole graphical interpretation. What we'd like to do is turn all of this information into a matrix. We'd like to turn it into a matrix. The thing is, though, in order to use a matrix, you are not allowed to have inequalities. It has to be equalities. So just imagine, previously, when we had an equation like 2x plus 3y equals 8, and then negative 1x minus 4y equals negative 5, those were equations, equalities, not inequalities. And then you just took all those coefficients and you put them inside of a matrix. So as a general rule, folks, just so we all agree, you can only put equations into a matrix. You cannot put inequalities into a matrix. So that begs our first question. How are we going to take all that information and put it into a matrix if, two of those are inequalities? This one's an equation, so that's fine. We can put that into a matrix. But the second two are inequalities, so we cannot put them into a matrix yet. So let me just ask you, how can I turn this into an equation? I have, this is a silly example, 2 plus 3 is less than or equal to 10. Does everyone agree? 5 is less than or equal to 10. What can I do? What else can I write on the board right now that I could replace this less than or equal to with an equal to sign? I want to replace that with an equal to. What would I have to do? I don't want to erase anything. I only want to write something more. I could add 5 to the left-hand side, right? And then it would be an equality. Okay? That's it. That's the whole idea. The whole idea for turning an inequality into an equality is that if you start with something like 5 plus 7 is less than or equal to 30, and I don't want an inequality anymore, what I would have to do is add in another term. And you might not know what that term is off the top of your head. You might just say, well, add something, okay, so that I can now call it equals. All right? And so is called a slack variable. A slack variable. Now, how on earth do we normally use the word slack? Maybe you've seen Back to the Future, and they call Marty McFly a slacker. Anyone remember that scene? They're always calling him a slacker because he doesn't do anything. How do you use the word slack? Hey, cut me some slack. Right? Like, stop being so rigorous with me and give me some slack. How else do we use the word slack? Maybe if you have a rope, and between like me and David, there's a rope and it's just loose on the ground, we would pull it tight, and then that would be taking up the slack. Anybody? Anybody? Are these the ways in which you use the word slack? Okay, well that's what this variable is doing. It's taking up the slack, right? So what you had, let me show this again, I'll just do these two. I had 5 plus 7 is less than or equal to 30, and so I threw in a variable right there so that I could then, instead of less than or equal to, I could make it equal to, and so we call that thing a slack variable. This is the beginning idea that we need in order to rewrite this, not as inequalities, but as equalities. All right, well, everybody is absolutely totally silent, so I'm just assuming that that's okay, and let's go back and look at number 1.
I need to do an example first.
Yeah, let's do an example. All right, so here we go, section 401. It says convert the inequality into a linear equation by adding a slack variable. So here's what your slack variable would look like. First of all, notice again, x1 and x2. These are our normal variables, okay? Normally, when we graph things, we use the variable y and x. But going forward, we might have lots and lots of variables. So instead of saying an equation like 2x plus 3y minus 4z, because I'm already out of the alphabet, right? I could either, if I needed more terms, I could start saying like plus 5a minus 6b. But some real life situations have hundreds of variables. So you'll run out of letters in the alphabet eventually. And so instead of doing all that, they just say 2x1 plus 3x2 minus 4x3 plus 5x4. And so we just use a system of subscripts, and you never run out of subscripts, right? So going forward, instead of using variables like x, y, z, we're just going to start using subscripts, x1, x2, x3, x4. These are the actual variables, okay? So let's just make a little note up here at the top. Fill this in with me. The actual variables that represent unknowns are going to be x of 1, x of 2, x of 3, etc. A slack variable, we are going to represent a slack variable which takes up the slack and turns an inequality into an equation. We're going to use the letter S, slack variable number 1, slack variable number 2, slack variable number 3. And so go ahead and rewrite this in your own handwriting once so you can feel this. If I have the inequality x1 plus 2x2, leave a little space, is less than or equal to 21, I would like to contribute a slack variable and turn this into an actual equation. So I would call this x1 plus 2x2 plus s1 is equal to 21. Okay, and that's a slack variable. All that slack variable did was allow me to change the inequality into equality. Now that's a benefit. Converting this inequality into an equality means we can now put that object into a matrix, and we can use matrix techniques to solve it, like inverse matrices. However, what became more complicated? We started with 2 variables.
Now we got 3.
Now we have 3 variables, right? So it's a trade-off, right? The benefit is now it's an equation. We can put it in a matrix. The downside is we just went from 2 variables to 3 variables. Okay, do it for the next one. We start with the inequality, x of 1 plus 4, x of 2 plus 3, x of 3. And we're saying that that's less than or equal to 139. But I'd like to be able to make that a row in my matrix, which means I need it to be equals. So I would change it to x1 plus 4x2 plus 3x3 plus slack variable 1 is equal to 139. Again, we just went from a 3-variable inequality to a 4-variable equality. Why? So that we can put it in a matrix and use matrix methods to solve. Alrighty? Well, let's try the next section. The next section, they're giving us the whole problem, right? we have our whole problem now in front of us. All this has to do is use slack variables to convert the constraints into a linear equation. So first of all, let's label everything. This first term right here, or I'm sorry, the first line, maximize that. That's your objective function. And remember, your objective function is your business objective. It's either your profit or your cost or what have you. Subject to, and then it lists a bunch of inequalities. Those are your constraints. Those are the inequality constraints that we'd like to rewrite as equations instead of inequalities. And then this last part, with x1 is greater than or equal to 0, x2 greater than, that's the non-negativity assumption. Meaning that these are word problems regarding business, and we can only be talking about a positive quantity of airplanes or peanuts or employees or anything like that. So now that we know what those parts are, all they want to know is, or what they want us to do right now is use a slack variable to convert the constraints into linear equations. So you'll notice we have two inequalities, and therefore we will need two slack variables. Each inequality gets its own slack variable. So the first inequality is going to, and watch how I set this up, because we want everything to be stacked. You know how whenever you have two equations on top of each other, you want to stack the x variable, stack the y variable, stack each variable. So this first one would be x1 plus 7x2 plus s1. That's going to be my slack variable for the first one. And that's going to be equal now to 15. Leave a little space. Because now the next inequality is 7x1 plus 3x2. The next inequality doesn't use the first slack variable. The first slack variable is only for the first equation. Now we're going to introduce a second slack variable into our second equation, and now that's equal to 25.
If I put a 0, like a space holder?
Absolutely. You can put a 0 space holder. That's a really nice idea. Absolutely nothing wrong with that. And in fact, we'll even go a step further, and we'll just go ahead and look at what that would look like as a matrix. What would that look like as a matrix? This isn't the final matrix we're heading towards. Our final matrix is going to be much bigger than this. But if you just wanted to put those two in a matrix, you would say, here's my matrix. My column headers would be x1, x2, s1, s2, and then the number at the end, right? So technically, we have 5 columns. And what would this matrix look like? If you put, a 1 in front of all those variables, you would have 1, 7, 1, 0, 15, and then 7, 3, 0, 1, 25. So yeah, the 0 placeholder is a great idea, Adon. Furthermore, look at that matrix that we just have, or that we have now. What do you see in that matrix?
Zeros and ones.
You see that nice little chunk there? That's the 1, 0, 0, 1 chunk. So automatically built into our matrices is going to be that Gaussian form that we tried to make in a previous matrix. The only difference now, that 1, 0, 0, 1 chunk is representing the slack variables. Okay, so try that again. Try number 4. All you need to worry about right now is just converting the constraints from inequalities into equalities. And write it down as an equation first, and then write it down as a matrix. And again, spread it out real nice. So the first inequality becomes 1.9 x1 plus 1.5 x2 plus 1 slack 1 plus leave a space, a placeholder like a 0, equals 30. And then the second inequality becomes an equation by writing 1.6 x1 plus 1.3 x2 plus no slack variable number 1 plus a slack variable number 2, and that equals 46. So then you take that whole thing and you could convert that into a matrix. And so your matrix would really be 1.9, 1.5, 1, 0, 30. and then 1.6, 1.3, 0, 1, 46. Now I'd like you to make a note about something right now. And you can write it in two different ways. Note. Each inequality gets its own slack variable. So when you're looking at S1, you can automatically say S1 represents the first inequality. S2 represents the second inequality, right? So the S1 and the S2 and the S3, those are labeling the inequalities that were in your constraints. So each inequality gets its own slack variable, and the number on that slack variable is actually telling you which inequality. Another way to write that is that you have as many slack variables as you have inequalities. And maybe that's totally obvious too. No, I'm not going to write that down. But it's just another nice way to think about it, is that you'll have as many slack variables as you have inequalities. So right off the bat, I'm looking, I see 2 inequalities. That means I need 2 slack variables. If I have 3 inequalities, I'm going to have 3 slack variables. How does everyone feel about that so far? Why did we do that? Why did we introduce slack variables to turn inequalities into equations? So that we can use matrix techniques. That's right, now we can use matrix techniques. You could take a matrix like that, plug it into your calculator, and calculate A inverse B, and whammo, you have the solution. All right? Okay. Next, find slack variables as necessary and write the initial simplex tableau for the problem. Oh, you didn't even see that. Okay, so everyone's looking at 5 and 6 now, right? You turn the page. Now I want you to look all the way up at the top and appreciate this phrase that they're giving us. We have a lot of cool words in this class, like Lagrange. Wait, what was another word that I really liked other than Lagrange? Okay, maybe it's just Lagrange.
Oh, it was the
D'Artagnan.
D'Artagnan.
Well, D'Artagnan, yeah, of course. Well, he's just one of the 3 musketeers. Well, he's not one of the 3 musketeers. The 3 musketeers are Athos, Porthos, and Aramis, but D'Artagnan was kind of like a little follower. Okay, so it says here, write the initial simplex tableau. Well, now, that's quite the phrase. Initial simplex tableau. So the initial, that just means the first thing you write down. Simplex tableau. Have we ever used the word simplex tableau before in our lives?
Nope.
Definitely not. You're not like, hey, hold on, I'm going to run down to Taco Bell and get myself a couple of simplex tableaus. Right? Probably not. So I pulled up the dictionary definition here so you can see it. This is an old idea. Not that old. I mean, this idea is only since maybe the 50s or 60s or 70s. So simplex is composed of or characterized by a single structure. So simplex, you might mean simple, means that there's just one thing. And what we're going to do is we take a problem like this that has an objective function, inequalities, and non-negativity assumptions, and we're going to turn it into one matrix. So that's what the simplex means. It's one matrix. But that one matrix has a lot of different things in it, right? You've got the objective function, and you've got the constraints, but we're just going to throw them all into one big matrix. Okay, that's simplex. And then tableau, a group of models or motionless figures representing a scene from a story or from history. That doesn't mean anything. Figuratively, literally picture diminutive of table. A table. It's a table. What's a matrix?
So
A table.
A one matrix table.
Yeah, exactly. I mean, it's just a table. It's a matrix table. It's one thing. You could just say that the simplex means one, and table is matrix. So,
What about initial?
yeah, initial means how you start the problem. How you start the problem.
You start the one matrix table.
Yeah. So, as in many things, we've got this really fancy word here, initial simplex tableau, which just means the matrix that you write down to start the problem. Okay, so now let's go take a look. Introduce like variables and write the initial simplex tableau. So what is this going to look like? Where's my eraser? It's in my hand. All right. Now, folks, they gave us a matrix thing right here. It's way too tiny. We're not going to write it down. Okay, what all do we want to write down? Now, first of all, this whole non-negativity requirement, we never have to include that in the matrix. It's just assumed. But we do want to put these other things into the matrix. And so how are we going to do that? First, we have two inequalities. So how many slack variables will we have? Two. So let's go ahead and start by making a matrix, a big long one. And let's make our column headers. Our column headers are going to be the variables, x1, x2. The slack variables, s1, s2. But then we also need to get z in there. Z is our objective function. We're going to throw a z in there. And then finally, we need that last column at the end to be our numbers. So look at that big, big, big matrix. Simplex tableau. One big, big matrix. Hey, that's what they should call it instead. One big, big, big matrix. Okay, so how will I put in 2x1 plus 5x2 is less than or equal to 8? I put 2x1 plus 5x2 plus the slack variable for that particular equation. You don't use the slack variable 2. There's no z variable in there, but it is now all equal to 8. I went straight from the inequality straight into writing it in the matrix. If it would be easier for you, you can also just write it down first. 2x1 plus 5x2 plus s1 equals 8, right? Because that's how you add a slack variable. This one would be 3x1 plus 3x2 plus s2 equals 11. But then we're going to put it down in the matrix. Okay, so my next inequality would become 3x1 plus 3x2. We don't use the slack variable for the second constraint. We do use this s2 slack variable for the second constraint. There's still no z variable, and that one's equal to 11. So again, folks, you'll notice the s1 slack variable is only used by the first constraint, and the s2 slack variable is only used by the second constraint. Okay, so now we have one row left, and we need to get this information about z. So everybody come over here now. We have, and instead of writing, that's what I want you to write. Z equals 4x1 plus x2. We need to write that down in such a way that it equals a number. Well, right now that's a variable, that's a variable, that's a variable. We need it to be equal to a number. So what we need to do is move the 4x1 and the x2 over to the left. So we're going to subtract 4x1, subtract the x2, bring it all the way over here to the left. So that what we have is negative 4x1 minus 1x2 plus 1z equals 0. We do that so that we can fit it into our matrix. So now what are we going to write down? Negative 4 under x1, negative 1 under x2, nothing under s1, nothing under s2, 1 for z, and then 0 for the number. That is the initial simplex tableau. Initial simplex tableau. What did we do? We just converted all of our inequalities into equalities, and we just threw everything into one big matrix. How do you feel about that right there? Michelle, go ahead, tell me your thoughts and feelings. Go ahead, you say something, then I'll say something.
Almost kind of.
Yep, that's it. And now we're about to do all sorts of computations on it, right? This is just the initial. This is how you start the problem. And I'll go ahead and tell you folks the goal. Do you want to hear the goal? It's a very simple goal. We just want to turn all the numbers in the bottom row positive.
That's it.
Bada boom.
I feel like there's more complicated.
It's very complicated to get to that point. But it's very simple to say the goal. We just want all the numbers in the bottom to be positive.
It's easy to say.
Easy to say, hard to do. Exactly right. So yes, this is the initial simplex tableau. And if you want to go ahead and write it down, the goal is bottom row all positive. By the way, every time I say tableau, I always think Rob Lowe. And then I'm reminded of how many chucks could a woodchuck chuck if a woodchuck could chuck wood. Because there's also one that goes, how many loaves would a Rob Lowe rob if a Rob Lowe could rob Lowe's? You know Lowe's like the Home Depot?
Yeah.
Yeah, there you go. Okay, so there's our initial simplex tableau. Our goal is to make the whole bottom row positive. And when we do that, like, do you want to just predict a little bit into the future about what will happen? When we're all done making that bottom row positive, just to predict into the future, you're going to have this right here, z equals a number. That's going to give you the maximum or the minimum value of the objective function. Okay, so just so you see where we're going, we're going to do matrix manipulations. We're going to make the whole bottom row positive. And the minute we make that whole bottom row positive, whatever you see right here, which is z, that's 1z, equals a number, that's going to be the max or the min of the objective function. Okay? Now, even as I say that, I realize that's like all magic. Like, who says? Who says? Just because I make the bottom row all positive numbers, that's going to be the max min. Well, the theory tells us that it's true. If you read the entire textbook, it goes into details and describes why this works. We're going to learn the method. Okay, so do the next one, folks. Again, don't use this thing. It's too small. So we're going to set up our initial matrix. Make sure it's tall enough for 3 rows, right? You need 3 rows. Constraint, z function. Maybe you want to label that a little better. Because the top row label, let me get out of the way of that. There we go. There we go. The labels on the top are x1, x2, and then we need a slack variable for both constraints, so s1, s2. And then we need the z variable to represent something. So we have z, and then finally we need the numbers at the far end. So when you make your matrix, make sure it's wide enough to handle all that information, and then tall enough to account for the fact that you're going to have constraint 1, constraint 2, and the z objective function. So maybe that's a little helpful now that you've got the rows labeled as well. So if you'd like, you can start by adding slack variables to the 2 inequalities. So the first inequality would be 2x1 plus x2 plus slack 1 equals 17. And then the second constraint would be 3x1 plus 5x2 plus slack 2 equals 80. And then you begin putting all that information in your matrix. Oh, did you just write it all in there, all teeny? Oh, there you go. You have it right there. Okay. Okay, so what do we have then? 2, 1, 1, 0, 0, 17. And 3, 5, 0, 1, 0, 80. And we do now have to take our, now maybe you can just do this in your head, right? You want to keep the z on the left and move those other 2 terms on the left. So you can probably just see that that's going to be negative 4x1 minus 2x2 plus 1z equals 0. Right? That's probably something you could do in your head without having to write it all down. But the key thing is you move all the terms left. Move left. So now what do we have? Negative 4, negative 2, 0, 0, 1, 0. Is that what that is? Okay. Okay. Any questions about what we've done? I'm not seeing all that. No. So sad. That poor thing. She did look a little tired.
Simone, we're here for you. Why don't you come back and talk to us?
All right. Folks, that's it. That's creating your initial simplex tableau. How many loaves could Rob Lowe rob if Rob Lowe could rob Lowe's? How do you think he feels about that? A cute little rhyme about him robbing a store. Okay. What's our next problem? Number 7. Let's Turn the page, take a look.
Still the bottom row is negative.
What?
Still the goal is to make the,
Bottom row positive.
yeah, but still it's negative.
Right now it's negative.
Oh, yeah.
Yeah, the
It's
goal.
negative.
The work we're gonna do. Yeah, okay, so folks, it says write the solutions that can be read from the simplex tableau. So here's a simplex tableau. You can tell that the original had 3 variables, 2 slack variables because there's 2 constraints, and the very bottom row represents the objective function. So first of all, let's just label what we have. This was our first constraint, that was our second constraint, therefore those were the inequalities, right? And then this bottom one is our z function, that was our objective function, right? And then all the way at the end here, those were the numbers that all those inequalities were equal to. So, first of all, this matrix is not the initial simplex tableau. Somebody already did some work on it. They wrote down the initial simplex tableau, they did some work, and now a couple things I want you to notice. First of all, do you see that bottom right-hand pair of numbers there? What that means is that currently, what they're looking at for z is that in this case, the current value of z is 16. That's just the current value of z. That doesn't mean it's the max or the min, because notice, is the entire bottom row positive yet? The entire row isn't positive yet. So this is just a value of the objective function. It's not completely maximized yet. It's not completely minimized yet. That's just the current value of the objective function for the corner point that they're looking at. Now, everybody, remember visually what we're doing right now. If you did take those 2 inequalities, right? If you took those 2 inequalities and you shaded the region and you looked at the corner points, one of those corner points would give you the maximum or the minimum. But if you're not, all the other corner points, not necessarily. Like say that this one is all about maximizing, then maybe at this corner point is z equals 12, and this corner point is z equals 13, and this corner point is z equals 18, and this corner point is z equals 16. So can you kind of see where we're at so far in the table? Right at this corner point. And so the current value of the objective function is 16. Is that the maximum? No, it's not yet. And how do we know? Well, visually, I know this one is actually the maximum. But also, because this whole row isn't positive yet, I know that I'm not there yet. Okay? Okay, so likewise, looking down here at this bottom problem, number 8, this is also the current value. You would just be the current value. Okay, we're not at the max or the min yet. This one, however, is this whole bottom row positive? Anyone?
Yes.
Yes, that is all positive. So actually, in this case, z equals 7 is the, well, it's either the maximum or the minimum, depending on what the problem is. But I'll just say the best. So if this was a minimization problem, we're saying 7 is the minimum. If this was a maximization problem, we're saying 7 is the maximum. And so that's where we read our answer. Okay, but now there's still more to get out of this table. So it says write the solutions that can be read. Remember how we needed to get to the value, we wanted the matrix to look like this. We wanted to get the matrix to look like that. Well, do you see anything at all in their matrix that looks like that? With a 1 and then zeros above and below it? Like this row, this column does not look like that at all. This column, no. Ooh, this one. That looks a lot like the Gaussian goal that we had before, where you want a single 1 and zeros. Where else do we have it? Here. These are the 2 columns through matrix manipulations that they were able to get to be a 1 with zeros. A 1 with zeros. Keep in mind, since this was a 2-equation matrix, you can only solve for 2 variables at a time. That's just a basic theory. That when you have 2 variables, if you have 2 equations, you can only solve for 2 variables. So like let's say that I had 2x plus 3y minus 4z and 3x minus or plus 2y plus 5z. There's a general rule that states that you can only solve for as many variables as you have equations. So if you only have 2 equations, you can only actually solve for 2 variables. And so in this case, we only had 2 constraints. So the most we can do is get 2 of our columns to look like the Gaussian goal of a 1 with zeros. So let's look at this then. What are we saying that this row means? This means that 1x3, everybody, did you already circle those? 1x3 is equal to what? 30. So the 1x3 is equal to 30. And then what about this one over here? This is stating that 1s2 is equal to 15. There's still more I have to say. I'm just kind of introducing us to how to read this information. Here's the last bit of information that you need. Since we're looking at how many variables? How many total variables are we looking at? 5. But since there's only two constraints, how many can we solve for? Only 2. So I'm just going to make a note. We have 5 variables, but only 2 equations. Well, I'm going to say constraint equations. Only 2 constraint equations. Because you might be sitting there saying, Mr. G, we obviously have 3 rows. But remember, the third row is the objective function, which is not an equation at all. That's just a profit or cost. So we only had 2 constraints. We have 5 variables, but only 2 constraints. So we can only solve for 2 variables at a time. I'll say at a time. And that's what we just found from the table. Those are the 2 variables that we actually solved for. Here's the last bit. Let all other variables equal 0. So what we're saying is we've got 5 variables. I can only solve for 2 of them. So just as like a temporary consideration, you let all the other variables, x1, x2, and s1, you let them all equal 0 so that they're just completely out of the playing field. So you say, I'm going to write it up here, let x1, x2, and s1 all equal 0. And if x1, x2, and s1 are all equal to 0, all of those columns drop out of the picture because they're all equal to 0. And all you have left is the s2 column. And that's why we're allowed to say 1x3 is equal to 30 and 1s2 is equal to 15. And that z is equal to 16. So provided that you let all those other 3 variables equal 0, then we have x3 is equal to 30, and s2 is equal to 15, and z is equal to 16. And that's what they mean, write the solutions that can be read from the simplex tableau. So again, this wasn't the initial simplex tableau. Somebody already did some work on it. They turned a couple of these terms positive. And as of right now, they're looking at a particular corner point, okay? Keep in mind now, this is 3 variables, so it's in 3 dimensions. We can no longer just draw a 2-dimensional graph of it. It's 3 variables, so it's 3 dimensions. But this represents a corner point. And we could even say that. Each simplex tableau represents a corner point. So every time you do work on it, it's going to represent a new corner point of your feasible region. And so you just keep on working the matrix, creating columns that have 0s and 1s. And every time you create 2 columns that have 0s and 1s, you're at a new corner point, and you can read off one of the solutions and the current value of the objective function. Okay, so folks, let's try that again. Now that we've heard all that, look at this next simplex tableau and find the columns that are just zeros and ones. Sadae, what's one column that's just ones and zeros? Yeah, x1 is 1. And what's the other one, Sadia? Yeah, S1. Now keep in mind, folks, we're not interested in Z. I realize that Z is also zeros and a 1, but the Z we're going to be looking at down that way. Okay, so far, what we're saying then is we're going to take x2, x3, and s2 out of the picture by setting them all equal to 0. So if x2, x3, and s2 all equal 0, then we've got x1 is equal to 3, and we've got s1 is equal to 9, and we've got z equal to 7. And that's what you can read from the simplex tableau. I know I just threw a lot at you. Like, that's how you read the simplex tableau. You look for the columns that have ones and zeros. At most, you're going to have as many columns as you have constraints. So again, notice that we had 2 constraints, so we have 2 columns that can be turned into ones and zeros. The other columns will all be treated as 0, so x2, x3, and s2 are all equal to 0. And then you can say what the other 2 variables equaled, and you can even say what the current objective function is equal to. Questions? Before we keep going? This is just how you read it. Again, the number of constraints is equal to the number of slack variables. The number of constraints is also equal to the number of columns that you can turn into ones and zeros. So that could be worth writing down somewhere as a reminder to yourself. All right, so I think I'll go over here. The number of constraints, that is the original inequalities, equals the number of slack variables, which also equals the number of columns you can make into zeros and a 1. We are learning a lot of. We haven't solved anything interesting yet. We're just trying to see what we can see from the table. Now let's see. I think that covers everything I wanted to tell you. All right, let's try another one. It says pivot. Okay, everyone on to the next page. All right. It says pivot once about the circled element in the simplex tableau. So everybody notice that this is the initial simplex tableau. How do I know? All of those values are negative. And that's what you would get if you solved for z and moved all those terms over to the left. That's your objective function. So we're looking at the original simplex tableau. We also know it because you've got this perfect grid of ones and zeros right there, which is representing the use of slack variables to turn the initial inequality constraints into equality constraints. So we are, in fact, looking at an initial simplex tableau right now. And when they say pivot, like that scene from Friends when Ross was trying to get everyone to take this couch up the stairs, pivot, okay.
Oh, yeah.
Pivot means make this column into 1, 0, 0. Okay, that's the use of the word pivot. Pivot means make it look like the Gauss-Jordan method. Okay, so it's either going to be 1, 0, 0, or 0, 1, 0, or 0, 0, 1. You're going to make that column look like that. And the circled number is what you want to be the 1. Okay, so we're about to do some really exciting work here, folks. Here we go. Here we go. This is really exciting. The excitement in the room is palpable. I can feel it. I have goosebumps. We're about to do some matrix manipulations to read a corner point. Okay, that's all we're going to find. We're going to find a corner point from our feasible region by pivoting. So let's do it. First of all, we want to turn this top number into a 1. We want to turn that into a
0,
and that into a
0.
All right. So how about we go ahead and get rid of
Everything.
yeah. We're going to get rid of everything. So since this is already a 2 and that's a 2, let's multiply the whole top row by -1. So this would become -2, -1, -4, -1, 0, 0, -48. I multiplied the whole top row by -1 so that I can add it into the second row, and that will turn that 2 into a 0. Okay? Let's go ahead and write real big here. My second row now is going to become 0, 3, -3, -1, 1, 0, and -16. Check my work, see if you agree. What I did was I multiplied row 1 times -1 and added it into row 2 in order to cancel the 2 and make it a 0. Lucy, did you already write it down? Okay, now what do we need to do? We want to cancel out that -1 to make it a 0. So what do we need this top number to be in order to add it into -1 and cancel it? Then we need to turn that into a 1. And we need to turn that into a 1 anyway because it's going to be the top 1. So now what I'm going to do is divide all those terms by 2. So that'll turn the top row into 1, 0.5, 2, 0.5, 0, 0, and 24. So I just divided the entire top row by 2. Incidentally, that is going to be our new top row. 1, 0.5, 2, 0.5, 0, 0, 24. Because we do want that first number to be a 0. And now we're going to add those numbers into the third row in order to cancel it out and get a 0. So 1 and -1 is 0. 0.5 minus 3 is -2.5. 2 minus 2 is 0. 0.5 plus 0 is 0.5. 0 plus 0 is 0. 0 plus 1 is 1. And 24 plus 0 is 24. Yep. What we just did is called pivoting. Why they chose the word, I don't know. But now, can we go ahead and read the table? Yes. We can go ahead and read the table. We have one column of 1s and 0s here. Where's the other one? Oh, wouldn't hurt to label everything. X1, X2, X3, S1, S2, Z, and the numbers. So we have one column of 1s and 0s here. Where's the other one?
S2.
Yeah, S2. Keep in mind, Z will often look like 1s and 0s, but Z isn't something we're trying to read. Z isn't a variable. Z is a function, and we read that one sideways, like this. So what we have now determined is that if we let x2, x3, and s1 all equal 0, so I'm going to write that down. If x2, x3, and s1 all equal 0, then what's the value of x1? Yeah, 24. x1 is 24. And what's the value of S2?
-16.
Negative 16. And Z is equal to 24. That's just the current corner point, okay? All this information represents a corner point. Is it the best corner point? Is it the best corner point? No, because not all the values in the bottom row are positive. We still have a negative value there. And so this does not represent the best corner point, but it is nevertheless a corner point, okay? I keep referencing my feasible region because we're in 3-dimensional space now. We're actually in 5-dimensional space. So we can't picture it, but we are still considering the same idea that each way that you read the simplex tableau is a corner point. And so that's a corner point. Okay. How about the next one? We don't have to do all of these as examples because we want to have time to do like a real full problem. But let's go ahead and try, how about I leave 10 for you? Because 10 is pretty simple, right? You can add the 2 into the bottom row, that'll become 0. And you can multiply 2 times -2 to be -4, that'll cancel that one. And then you can divide the whole top row by 1. Does everyone want to just try that one right now? How about everybody just go ahead and try number 10 right now? Let's do now. Go and do it now. Your whole goal is to pivot that column. Turn that column into 1, 0, 0. Good, nice start. You got it all labeled. So first you want to get rid of first. You turn the form to 0, turn the negative to 0. We'll do the bottom one first. You just have to add this whole row into the bottom row. And the 2 plus the 2 will be 0. And 0 plus 0 will be 0, and keep going. Wait, oh yeah, you're on this one. Okay. Yeah, nice.
Changing it ourselves to 1, 0, 0, first column. Yeah.
What are you saying though?
Oh, just you got lost for a second.
Oh, okay. Yeah, so where are you going to start these? You want to turn both of those into 0, and then into 1, 1.
Okay.
So I would start by making that a 0 by just adding the entire top row into the bottom row. Because then the 2 plus -2 will cancel out. All you're worried about is this column right here. I want this to be 1, 0, 0. Okay, so if you'd like to follow along, I know some of you are in the middle, some of you are towards the end. Around the 2, we want to turn this into 1, 0, 0. All right, that's our goal. We want this to become 1, 0, 0. So since these are all multiples of 2, I'm not going to turn this one into a 1 yet. My goal is to turn these into zeros first. And the -2 would be the easiest to turn into a 0, because if I add 2 plus -2, I get 0. So I'm going to go ahead and add the top row into the bottom row and see what I get. So I'm going to add the top row into the bottom row. So 0 plus 0 is 0. 2 plus -2 is 0. 1 plus 0 is 1. 1 plus 1 is 2. 4 plus 1 is 5. 0 plus 1 is 1. And 6 plus 0 is 6. So I literally just went through and added the entire top row into the bottom row. Now I'd like to get rid of the 4. What do I need my circle number to be to cancel with a positive 4?
-4.
I need that to be a -4. So what am I going to multiply the whole top row by?
-2.
-2. So multiply the whole top row by -2. So that would give me 0. I got to erase that. That would give me 0 times -2 times -2 times -2 times -2 times -2 times -2. There, I just multiplied the whole top row by -2. And now I can add the top row into the middle row. So 0 plus 1 is 1, -4 plus 4 is 0, -2 plus 0 is -2, -2 plus 1 is -1, -8 plus 2 is -6, 0 plus 0 is 0, and -12 plus 10 is -2. Now I want my top number to be a 1. And so now I just divide everything by 2, because I want that to be a 1. So I divided the whole top row by 2. So 0 divided by 2 is 0, divide by 2, divide by 2 is 0.5, divide by 2 is 0.5, divide by 2 is 2, divide by 2 is 0, divide by 2 is 3. Now keep in mind, our goal was to pivot around the 2. Our goal was to create this. But you'll notice, as a little bonus, that another column appeared now as 0s and a 1. What's the other column that appeared? The first one. Because basically, anytime you pivot one row, you're going to get another one. So let's label all of our columns now: x1, x2, x3, s1, s2, z, and a number. And we can now read off our answers. You'll notice I circle everything that's relevant. I circled my 2 columns that were 0s and 1s. I circled my z answer. And remember, we're going to make all the other variables become 0, so I'm going to cross them out. x3, s1, s2, those are all equal to 0. And so let's write down what we know. We know that if x3 is equal to s1 is equal to s2 is all equal to 0, so we're taking those variables out of consideration, then x1 is equal to -2, x2 is equal to 3, and z is equal to 6. Now, what do we notice about that corner point? What? Well, it may or, oh, yeah, good point. All the values along the bottom are positive, so it's the max or the min, depending on what the problem represented. But we'd also notice that our x value is -2. We're not considering x values that are negative. Right? We had that whole non-negativity assumption that we're talking about things like airplanes and products. So even though that's a feasible point, it's kind of like what we had here was a feasible region. It was like this, and that corner point was over here. So we actually wouldn't consider that as part of our solution anyway. And we would then need to go find a corner point that was actually in the first quadrant. Anyway, that's just a totally separate consideration, just something to be mindful of, that we are looking for solutions that are positive. In any case, we did it correctly. Okay, in the interest of time, we'll skip number 11. You can just cross it out. Simone, you can cross out number 11. And let's consider some word problems now. Okay, so everything we've done so far is just mechanics, right? We just talked about a bunch of mechanics, the manipulations. Now we can actually start solving some word problems, which is life. All right. Ready? A bakery makes sweet rolls and donuts. Et cetera, et cetera, et cetera. Okay. The bakery has et cetera, et cetera. Wait, what's our question? Oh, to maximize profit. So first of all, set up the initial simplex tableau to maximize profit. So we know that our objective function is going to be profit. So that's one thing we need to come up with. But we also need to figure out how to label our matrix. What are the column headers? What are the row headers? So let's see here. The baker makes sweet rolls and donuts. Would it be fair to assume that the sweet rolls and the donuts are the variables? That the question is going to be how many sweet rolls should we make and how many donuts should we make to maximize profit? So let's go ahead and say that if our x1 and our x2 are sweet rolls and donuts. Does everyone agree so far with what we're doing? So a batch of sweet rolls requires flour, eggs, and sugar. A batch of donuts requires flour, eggs, and sugar. The bakery has 600 flour, 740 eggs, and 760 sugar. Where do those numbers go? That represents the total amount of supplies that the bakery has. Where should those numbers go?
Next to.
Those are our total numbers. Next to where?
At the end.
Yeah, they go all the way at the end. So our totals go all the way to the end. So that's 600 of flour, 740 of eggs, 760 of sugar. Now we know what to title our rows. So that is flour, and that is eggs, and that is sugar. Our matrix doesn't actually end there because we're still going to put our objective function at the bottom. But that's what we have so far. So now back to the beginning. A batch of sweet rolls takes 3 pounds of flour, so that's going to be 3x1. Wait, what does it say? 1 dozen eggs? So 1x1. And 2 pounds of sugar, so 2x1. And then, now we're going to go talk about donuts. So the donuts require 5 pounds of flour and 3 dozen eggs and 2 pounds of sugar. Okay, I made my matrix too narrow. I don't know about you, but you might have to rewrite this. I need to put mine out much further. 600, 740, 760. Those are my totals. Because what do I still need room for?
S1, S2.
Yeah, I still need my slack variables and my z. Now, how many constraints do I have?
2, 3.
3 constraints. Therefore, how many slack variables will I have?
3.
3. So I'm going to need my slack variable 1, slack variable 2, slack variable 3, and then I still need to fit z in there to represent my profit. So my flour constraint is going to be plus 1 S1 plus 0 plus 0 plus 0. And that's equal to 600. And then my egg constraint is going to be 1x1 plus 3x2 plus 0 plus 1s2 plus 0 plus 0. And then my, oh geez. And then my sugar constraint is going to be 2x1 plus 2x2 plus 0 plus 0 plus 1s3 plus 0. And then finally, we need to put in our objective function. So how do we build our objective function? The profit says the profit on a batch of sweet rolls is 138, and the profit on a batch of donuts is 53. So the sweet rolls represents x, so that's 138x1, plus the donuts is 53, so that's 53x2. So that's our objective function, which is profit, which is z equals all that. And so remember to put z into our matrix. we need to move the x1 and x2 terms to the left. So if you rewrite that, that would really be negative 138x1 minus 53x2 plus 1z equals 0. So now we need to throw that down all the way in the bottom. Negative 138 x1 minus 53 x2 plus 0 for the slack, 0 for the slack, 0 for the slack, plus 1z equals 0. It says set up an initial simplex tableau. So there we did it. That was our initial simplex tableau. Although not really, because I have all my variables in there. What would it really look like? We would need to just put in the numbers with the row headers. So let's see if, gosh, I feel like I would need more space to make my final answer. See, what we just wrote was kind of sloppy, right? So now we'd want to take a moment to really do it well. And so we'd say, okay, I've got x1, x2, s1, s2, s3, z, and a number. And so then I would have my 3, 5, 1, 0, 0, 0, 600. And then 1, 3, 0, 1, 0, 0, 740. And then 2, 2, 0, 0, 1, 0, 760. And then negative 138. Negative 53, 0, 0, 0, 1, 0. Ah. Okay, folks, that's what your initial simplex tableau would look like. Initial simplex tableau. One big matrix that contains all the information of the entire problem. What is the information? These were the constraints. Well, I'll write it this way. Constraint number 1, constraint number 2, constraint number 3, and the objective function.
Cool.
Yeah, very cool. Now, do you notice what this whole big chunk looks like? Yeah, it's that Gauss-Jordan format, right? With the 1s and the 0s. Is that always going to be the case? Yeah, because every constraint gets a slack variable, and then you get the z at the end. So we know right up front that when we build this whole massive thing, you're going to end up with one big old Gauss-Jordan grid of 0s and 1s right there. You'll have your totals there with a 0. And then over here is where you just put in all the coefficients from your constraints and the negative coefficients of your objective function. So there is a method to the madness that you could almost now that you see how it's done, you could do that much faster by kind of knowing where everything goes.
Is that the answer?
That's the initial simplex tableau.
Okay.
That's the answer to that problem, because all they wanted us to do was set it up.
Okay.
If we wanted to solve it, right, what would we do? We need to turn these numbers positive. We need everything here to be positive. Well, how would we do it? By pivoting. We would choose a number to pivot. And by pivoting once or twice or maybe 3 times, we'd eventually get all these numbers positive, and then we'd be able to read off the maximum at the very end. Okay. Now I know my phone just went off. Let's just see where we are here. Oh, this is wonderful. Okay, we're ready to go now, folks. We are now at a problem where it says, here's the initial tableau. Go ahead and solve the problem. This is very exciting. Should we do one before we take a break, or should we take the break now and let your brain marinate?
Let my brain settle.
Okay, let your brain settle. Everybody take a break. The time is 3:20. Be back at 3:30. 3:30. And then we're going to do some serious matrix manipulations. Oh, there we go. Yeah, I know. No, I understand. Thank you. Thank you, Ms. Cheryl. I meant to ask you about that today. Don, that was quite the side.
I'm getting old.
There you go.
You can flip that.
All right, folks, it's 3:30. Let's do it. We are about to solve a problem. So it says the initial tableau of a linear programming problem is given. So if you want to go ahead and label everything with me real quick, we know this is constraint 1, this is constraint 2. That's why we have slack 1, slack 2. We know that this represents our objective function, and that's where the z variable actually is located. And it says to use the simplex method to solve the problem. So at a bird's eye view, what we're going to do, let's remember our goal. Our goal is last row is positive. Right, so we want all those terms to be positive. In order to do that, so our method is that we are going to choose various values to pivot. Right, we're going to pivot around certain values. Now the big question here is, which value do I pivot around? Okay, because notice these three, the last three, the slack, and the z, those are already pivoted. That's not very interesting. So what we're left wondering then is, which of these values do we pivot? Okay, so we need to choose one of the actual variables to pivot around, and it needs to be one of the constraints that we pivot around. So how many different choices do we have for a pivot?
6.
6 different possibilities. One of those pivots is going to yield the result that this bottom row is positive, and we're going to get our answer for z equals the value of the max to the min. So do we want to just try all 6 pivots?
No.
No. That would take a very long time, right? So what I'm about to show you is the method, the algorithm for figuring out which of those values to make your pivot. So keep in mind, this method I'm about to show you is going to tell you, aha, pivot this one. Or, aha, pivot that one. Right? That's what we want to know, instead of just trying them all at random. Okay, so we're going to have to write down some instructions. Everybody, write down some instructions. I have to admit, they're rather lengthy instructions. Okay? So find somewhere off to the side, maybe even the whole right-hand side of your page here, we're going to write down our instructions. 1. Oops. There we go. 1. Step 1. Choose the most negative number in the bottom row, and if there happen to be 2 numbers right in a row that were the same most negative number, you choose the one furthest left. Okay, so in our particular case, what's the most negative number here?
-4.
Thank you, Diego. -4. So that's the most negative number. So now already what we know is that this is going to be our pivot column. We're going to pivot this column. But what we don't know yet is which of these to pivot. Do we pivot around this one and make it 1, 0, 0? Or do we pivot around this one and make it 0, 1, 0? We don't know yet. So now we'll move on to step 2. Form all quotients of that column with the last column. Okay, now what that means, let's do it in context. We're considering this column right here. So we're considering this column. We just don't know which one we're going to turn into a 1. And what we're going to do is make a quotient with these numbers and the numbers in the last column. So we're going to take the last number and divide it by the number in the column we're interested in. So we're going to do right divided by left. Right divided by left. So I'm going to go ahead and start this one. I'm going to say 18 divided by 2, which is 9. And I'll do 8 divided by 1, which is 8. Right now, this might seem like black magic. Like, okay, why are we doing this? What's the purpose? It's the algorithm. It's the algorithm that has been proven to work. So you form all quotients, right divided by left. I won't even make a note to yourself, right divided by left. And what we're going to do is disregard any zeros or negative numbers. Okay, it just so happens that both of our numbers turned out to be positive, so we're fine. But if you did a division and you got 0 or a negative number, you would just disregard that completely. And what you're going to do is from those two, choose the smaller to be your pivot row. And technically, it's choose the smallest one, but if they were both the same, they'd be equally small, so choose the one furthest up. Furthest up. So which one of our numbers was smaller? Which one of our quotients was smaller? 8. So now we know that this is going to be our pivot. We just chose the correct pivot. Step 3, pivot. So actually do the pivot. So we're going to actually do the matrix manipulation to turn that into a column, which is 0, 1, 0. And we might as well just write the last step. 4. If the whole bottom row is now positive, you're done. If not, repeat the whole process. You start over from number 1 and choose the most negative number furthest to the left and start over again. Okay, so this is our algorithm that tells us how to choose the correct pivot to get the bottom row all positive so that we can find the right value for Z. Okay, everyone, so let's pivot once. We want to turn this into a 1. It already is. And we want to turn that into a 0 and that into a 0.
Alrighty.
Alrighty, indeed. So I'm going to start by turning the top 2 into a 0. If I want the top 2 into a 0, I need to turn my 1 into a negative 2. So I'm going to multiply the whole second row by negative 2. So that becomes times negative 2, 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 times negative 2. So I just multiplied my entire second row by negative 2, because that way I can add that second row into the top row, and it will make that 2 into a 0. So now I have negative 1, 0, negative 6, 1, negative 2, 0, and 2. So we multiply the entire middle row by -2 so that we could cancel the 2 above the 1, the -0. Incidentally, the second row can stay just like it is. Because I want to pivot, that means make it a 1. It already is a 1, so the second row can just stay. Now remember, our goal is to make this whole column here. So this is x1, this is x2, this is x3, this is slack 1, slack 2, z, and a number. I still need to make this one a 0. So that's a -4. What do I need to turn my number into?
4.
+4. So 4 times 4 times 4 times 4 times 4 times 4 times 4. And now I'm going to add that all into the bottom row. So that would be 7, 0, 18, 0, 4, 1, 32. And you'll see, first of all, that we succeeded in pivoting. We created a 0, 0, and a 1. Not only that, but you'll find another variable that is also 1, 0, 0. There it is. And you'll notice that the entire bottom row is positive, which means we're done, which means that we've now identified our best value of z, and we can read all this information off of the table. So what we're going to say then is that if x1, x3, and s2 are all 0, so if x1, x3, and s2 are all 0, then x2 will equal 8, slack 1 will equal 2, and z will be optimized at 32. That's the optimal value of z. And that's it. I hope you felt like that was okay. It didn't. You notice we didn't have to pivot twice. If any of the numbers had still been negative, we'd have had to start all over again and do that process all over again. But since all the numbers are positive, we're already done. So let's try it again. Let's look at number 14. We want to pivot. We want to choose the right pivot, first of all. So which one of these numbers should we pivot around to create the whole bottom row positive, and we can read off our z value. So step 1, choose the most negative number in the bottom row. Well, the most negative number is -3. So we know that the pivot will be this column. Step 2, form all the quotients of that column at the last column where we do right divided by left. So that means we're going to do 10 divided by 2, which is 5, and 15 divided by 1, which is 15. And we want to choose the smallest of those, which is definitely 5. So this is our pivot column. This is our pivot row. So this is our pivot number. Right? Because we're pivoting this column, and we're going to pivot this row. So that's the actual number that we're going to pivot. Now we'll go ahead and pivot. So we want that to be a 1. We want that to be a 0, and that to be a 0. Now notice, in this particular case, since we want to cancel that 1, we need that to be a -1. And since we want to cancel that -3, we're also going to need that to be a 3. So we might as well, in this case, go ahead and just divide this whole row by 2 to just turn that into a 1. And that could be our most quick way of canceling out the 1 and the -3. So let's go ahead and draw a whole new matrix after having divided the whole top row by 2. So that's going to give us a 1, a 1, a 0.5, a 0.5, a 0, a 0, and a 5. And I think it'd be best to rewrite everything. 1, 2, 3, 0, 1, 0, 15. And -3, -2, -1, 0, 0, 1, 0. And now we want to get rid of the 1 and get rid of the -3. And remember, you might want to circle it to remind yourself this is our pivot. So how do we get rid of the 1? We have to make this a
-1.
-1. So I'm going to multiply the whole top row by -1. So -1, -1, -0.5, -0.5, 0, 0, -5. I'm going to add that into the second row. I'm going to come over here now and write my final answer. So the top row gets to stay the same. 1, 1, 0.5, 1, 1, 0.5, 0.5, 0, 0, 5. I should label everything. X1, X2, select X3, select 1, select 2, Z, and a number. Okay? And now we're going to add that into the second row. So that gives us 0, 1, 2.5, -0.5, and 10. Folks, this is mind-achingly particular work, isn't it? It's so easy to make a mistake. Okay, now we want to cancel out the -3. So that means we need this to be a +3. So we're going to multiply the whole top row by 3. So the whole top row by 3. So 1 times 3 times 3 times 3. 0.5 times 3 is 1.5, so times 3 times 3 times 3 times 3. Now we're going to add that into the bottom row. So 3 and -3 is 0. 3 minus 2 is 1. 1.5 minus 1 is 0.5. 1.5 plus 1.5. 0 plus 0. 0 plus 1. And 15. So first of all, is the whole bottom row positive?
Yes.
Yes, so that means we're done. So we can identify everything that we can read from this. We have this column with 1 and zeros. This slack 2 is a 1 and zeros. We have our Z that we can read. And we're going to say that X2, X3, and S1 are all 0. So now it's just a matter of recording our answers. So again, we say if X2, X3, and S1 are all equal to 0, then X1 is equal to 5, and S2 is equal to 10, and most importantly, Z is equal to 15. And that is the optimal value of Z. All right, so what was that? 13 and 14? All right, great. So, I tell you what, 15, we can skip. Just for the sake of class time. You might still have a homework problem like that on my math lab, but for the sake of class time, it's just one more practice, and it's a little taller, but you would still do it the same way. Do you just want me to help you set it up to choose your pivot? Do you all want to make sure that we choose the right pivot? Yes, Mr. G, let's all check to make sure we choose the right pivot. All right. Let's check to make sure that we've chosen the right pivot. So at number 15, step 1, choose the most negative number from the bottom row, which is -5. So we know that's our pivot column. Step 2, form all the quotients, right divided by left. So that would be 8 divided by 2 is 4, 3 divided by 1 is 3, and 20 divided by 4 is 5. So the smallest number is 3. So we now have our pivot column, our pivot row. This is our pivot number. So that's your pivot number.
and you'll pivot around that number.
All right, so notice 15. Okay, doing great. Let's do 16. You'll notice that now 16, they're starting us from scratch. This is what you would expect to see in a regular homework problem. So they're giving you the objective function to maximize, they're giving you your constraints, and they're saying, hey, find the solution. Now keep in mind that right now you could fall back on the graphical method. You could fall back and say, hey, let's just graph this thing. So that would be something like y is less than or equal to negative 1/2 x plus 3 something, and y is less than or equal to negative 1/2 x plus 3 again. And we would have something that looks like this. And then we would find all of our corner points and shade it in, and then plug all the corner points in, and you find your answer, right? Or you can just treat it like a matrix. So you would begin. Let's do this whole thing. First, I'm going to write my equations down right here, just so I can see that. So my z equation becomes negative 5x1 minus 3x2 plus 1z equals 0. So I turn that. I turn my first constraint into an equation by adding a slack variable. So I have 2x1 plus 4x2 plus 1s1 equals 13. And my second constraint is 1x1 plus 2x2 plus 1s2. My second slack variable is equal to 6. And so far, those are all my equations. But what I really want to do is turn that into a matrix. So what will my matrix contain? It'll have x1, x2, slack 1, slack 2, z, and a number. All right? That's what we just found out by looking at our, turning those inequalities into equations. Now keep in mind you put your constraints on top and your z on bottom. So my first constraint would be what? 2, 4, 1, 0, 0, 13. And my second constraint would be 1, 2, 0, 1, 0, 6. And then my third and final line is always the objective function. And my objective function will be negative 5, negative 3, 0, 0, 1, 0. Now again, you might have just watched me go through that whole process and said, Mr. G, the 2, 4, 1, 2 goes right here. And the 5, 3 become negative right here. And this just becomes a Gaussian grid of zeros and ones. And then the 13 and the 6 go right here. And yep, that's the kind of like the shortcut. You could just know where to put all those numbers. But setting it up and really knowing where you're putting everything is better. Okay, so now what do? We created our initial simplex tableau. Everybody has one? You can go ahead and go to town, start doing your 4 steps. Find the pivot column, find the pivot row. So step 1 says choose the most negative number. That would be negative 5. Then in that column, make all of your quotients. So my quotients will be 13 over 2, which is 6.5. It's not a negative 2. And then 6 over 1, which is just 6. So the smallest number there is 6. So we now know my pivot column and my pivot row. So we want to pivot this number. That's convenient. That's already a 1. So now we just need to turn that into a 0 and that into a 0.
Multiply by negative 2 and 5.
Yeah, you'll do -2 first to cancel the top, and then 5 second to cancel the bottom. So I'm going to start keeping track of my final answer over here. And I better write in all those numbers. So first I'll multiply all the way through by -2. So times -2 times -2 times -2 times -2 times -2 times -2. I'm going to write in that answer. Add that into the top. So 0, 0, 1, 2, 0, and 1. I get to keep my middle row because that's already a 1 that I want. And then for the bottom, I have to cancel a -5, so I multiply the whole row by 5. So times 5, times 5, times 5, times 5, times 5, times 5. So adding that into my bottom row, I get 0, 7, 0, 5, 1, and 30. And it worked. The whole bottom row is already positive. I've got 2 columns that are 0s and 1s. So this is x1, x2, slack 1, slack 2, z, and a number. And we can read off all of our information. So for this particular problem, you would say, provided that if x2 and s2 are both equal to 0, then x1 is equal to 6, slack 1 is equal to 1, and z is equal to 30. Now I want you to notice, we're going to solve this problem the whole way through. What do we actually want to know? We want to know what values will maximize our objective function, right? And now we know that our objective function is going to be 30. So we know that 30 is the maximum value of z. Do we know what x1 and x2 are? We actually only know what x1 is. What's x1? We just solved it. 6. But what about x2? Our goal is actually to know the value of the 2 variables that maximize this function. So now, in our objective function, we know it's 5 times x1 plus 3 times x2. We still need to solve for x2, right? Like, these slack variables, we found out that x1 is 6 and the slack variable is 1. Slack variables are just slack variables. They're just these things that we invented to help us turn inequalities into equations. In order to solve the original problem, remember x1 and x2 represent airplane 1, airplane 2, or sweet rolls and donuts. So we need to still be able to tell the company what we actually solved for the best coordinate in space. So if x1 is 6, what does that force x2 into being? 0. Yeah, right, because 5 times 6 is already 30. And if we're saying 30 is the maximum, and that's already 30, then it must be that x2 is equal to 0. So does everyone agree that we now also know the value for x2? And we want to add that into our final answer? x1 is 6, x2 is 0. This is technically what we were looking for all along. What we wanted to find was find a value for x1 and x2 that will maximize this objective function. Now we can really confidently state we can maximize the objective function with a maximum value of 30, provided that you make 6 x1s and 0 x2s, whatever those are. Whether they're sweet rolls and donuts or airplane 1 and airplane 2. It's not enough to write down something about the slack variable. You actually then have to go back, finish the problem, and find out what the other variable is. And you can often do that by just using the objective function to solve for the other variable. And that would be the easiest way. Hey, folks, just so you know, we've arrived. Right? Like we've arrived. We've We're using this method. This is the method. There is one more twist at the end, okay? Like we still have to get to section 4.3. But this is the method. This is what chapter 4 was all about. It's called the simplex method. So everything that you just did was called the simplex method. That's the whole method. And so you figure out how to maximize or minimize an objective function by using this thing called the simplex method. Do you feel amazing? You feel so good? You're like, oh my gosh, this really made my day better. Well, your faces are so hard to read.
It's our poker face.
Yeah, apparently. I mean, I'd be really curious. I mean, what are you really feeling right now? What do you think about it?
Hatred towards man.
Hatred towards man? Yeah, I mean, really, honestly, I'm curious. I'm curious to know how you feel. Like, how do you feel about this methodology? Would you rather just go back to doing it graphically? Like graphically, you know, you can just take those inequalities just as they are and just graph them, find corner points, plug all the corner points into the objective function, and then you still find the answer. Or do you like this whole idea of taking this information, throwing it into one big matrix, finding a pivot point, and then reading the information off the table, and then backfilling to find x2? I mean, this is how people make these decisions. It's one of the two methods. Does anyone want to share any more feelings other than that, Tom? Michelle, how are you feeling about this?
Good.
Can you go home soon? Close, right? Okay. David, what do you want to say? Is this definitely one of the most random, weird math techniques you've ever learned in your life? I think so. All right, well, let's try another one. That was 16, right? So we've got 17, and then we're going to move into the last part. So let's try 17. We'll just try this one more time. Just really nail it down. Number 17. So we want to maximize this objective function, which represents profit probably, since we're maximizing, it must be profit, subject to these constraints, and let's turn it into an initial simplex tableau. So first of all, we know that our objective function, we have to move the x terms to the left, so it's negative 3x1 minus 2x2 plus 1z equals 0. We also know we have to add slack variables to our two constraints, so it'd be 2x1 plus 3x2 plus a slack variable equals 4, and then 4x1 plus 2x2 plus a different slack variable equals 12. All of those into an equation equaling a number. And now we can go ahead and fit it all into a matrix with x1, x2, slack 1, slack 2, z, and a number. So we start plugging all that in. Make sure you do the constraints first, and the z goes on the bottom. So our constraints are 2, 3, oops, I meant to write x2. 1, 0, 0, 4, and then 4, 2, 0, 1, 0, 12. And then my objective function goes last, negative 3, negative 2, 0, 0, 1, and 0. So remember, our goal is to get the whole last row positive. Our method is to choose a pivot. And how do we choose a pivot? Those steps over there. So first, choose the most negative number. That's negative 3. Then form all the quotients. So I'm going to do right divided by left. So 4 over 2 is 2. 12 over 4 is 3. So my smallest quotient is 2. And so my pivot number is this column in the top row. That's my pivot. Goody gumdrops. We have to cancel the 4. We have to cancel the negative 3. And we have to turn that into a 1. So what would be easiest? Let's just think. How do we cancel a 4?
Do we find the common denominator?
Well, we could find a common denominator for the 2 and the 3. Let's think about the 4 first. If you cancel a positive 4 with a
Negative.
-4. So that'd be easy to go ahead and make that a -4 because you can just multiply by -2. But if you want to cancel a -3, you need a +3.
+6.
Or you could turn the whole, you could multiply that whole row times 2 and then make that a +6. Or you could cancel the 4 first, because that'd be easy right now. Then go ahead and divide this whole row by 2 to make that a 1. And then once that's a 1, you could cancel the -3 by multiplying by +3. I mean, honestly, folks, it's whatever you want to do. It's however you want to do these matrix manipulations. I am going to first cancel the 4 with a -4. So I'm going to multiply the whole top row by -2. So that's times -2, times -2, times -2, times -2, times -2, times -2. So now I'm going to cancel out my middle row. So that's a 0. 4. 1, 2, 4. Now I want to be able to cancel a -3. So my preferred choice, I'm just going to go ahead and divide this whole top row by 2 because I want to turn that into a 1 anyway. So I'll go ahead and divide the whole top row by 2. So that'd be 1, 1.5, 0.5, 0, 0, 2. And now that I have that top row like that, I want to cancel the -3 with a +3. So I will multiply my whole top row by +3. So that'd be times 3, times 3, times 3, times 3, times 3, times 3. Now I can add that into my bottom row to get my 0, 2.5, 1.5, 0, 1, and 6. Now, folks, you could have done that in your own way. The good news is whether you do it your way or the way I just said, we're both going to end up with the same answer. You've got this pivot column. You also have this column to look at. And then you also have your z value to look at. So I'll give you a second to catch up on that. All right, so did you write down your final solutions? What do we have then? We're saying, I'm going to write it over here. I'm also going to label my headers, x1, x2, s1, s2, z, and a number. So what this tells us is that if, I'm going to cross them out, x2 and s1. So if x2 and s1 are both equal to 0, then x1 is equal to 2, and slack 2 is equal to 4, and z is equal to 6. Did everyone get that? All right, now remember, we're not done yet. The actual problem is to find the values of x1 and x2 that maximize z. So now that we know that z is 6, we can write down z equals 3x1 plus 2x2. We know that z was 6. We know that x1 was 2. And now we can solve for x2. So that's 6 equals 6 plus 2x2 The 6's cancel out, and we have 0 equals 2x2, which tells us that x2 would have to be 0.
That's that process.
Oh, I guess we already knew that, didn't we? Yeah, okay, well, good point. I didn't know. We could have just known that because x2 is equal to 0. No, I guess in this case you didn't have to do this. Not every problem is going to end up so simple that x1 has a value and the other one is 0. So you just have to be careful and double check. But yeah, good point there, David. I guess that one was a foregone conclusion. Okay. In the interest of time, can we do this one? I think we can do this one. This is just one big long problem where you read the information and just circle your multiple choice answers. It's kind of a nice problem because it just kind of tests everything that we know. So let's just look at it together. The manufacturing company wants to maximize profits. Oh, of course, maximize profits, why not? On products A, B, and C, the profit margin is $3 for A, $6 for B, and $15 for C. So right up front, which product do you want to sell more of? In terms of profit, which product is most profitable? Yeah, product C, because every time you make product C, you're making the most profit. So you'd be very motivated to sell a lot of product C. The production requirements and department capacities are as follows. So you have various departments, assembling, painting, and finishing. You've got the 3 different products, A, B, and C, and then that's the total number of hours you have for each department. So you only have 30,000 hours for them to assemble the stuff, 38,000 for them to paint it all, and then 28,000 for them to finish it all. And furthermore, this is the hours that it takes for each one of these products. So product A takes 2 hours of assembly, 1 hour of painting, and 2 hours of finishing. Likewise for B and C. Okay, so what are the coefficients of the objective function? Well, first of all, what is the objective function? They didn't give it to us. What would the objective function be? Everyone write it down. Objective function would be profit, which is what? What is the profit that we're making from each of the 3 products? Anyone want to say? How much profit do we make from product A?
$3.
So 3A plus, how much profit do we make from B? 6B plus 15C. So the coefficients on our objective function is 3, 6, 15. All right, so there's our objective function. That's how much profit we're going to make for each of the products that we make. How about number 2? What are the constants in the model? The constants are the numbers. Those are the totals at the far right. What are our constants? 30,000, 38,000, 28,000. Those are the constants. Another word for constants is totals. Those are the totals for what you have to deal with. What is the constraint for the assembling department? So what is our constraint for assembling? This would be 2x1 plus 3x2 plus 2x3, all has to be less than or equal to $30,000, right? Or no, 30,000 hours. Or instead of x, it could be a. So 2a plus 3b plus 2c is less than or equal to 30,000. So which one is that? It's not that one, or that one. It's 232. Is it D?
Yes.
Yeah, that's the constraint. Okay, what's the constraint for the painting department? Well, you can figure out the next 2. Last one, what is the maximum profit in this model? Well, that would mean actually 3 actually means sit down and solve the whole thing. But let me see what time it is. We have 30 minutes. Let me look at my answer key real quick and see how long the problem is. To be fair, you only have to pivot once. I think this would be a good problem for us to do. Yeah, this would be a good problem for us to do. We only have to pivot once, and we can solve it. So, how do we set up our model? You need a lot of space. Do you have a lot of space at the bottom? Yes, you do. So, let's go ahead and jot down now. We're going to stick with x1, x2, x3, not a, b, c. So we've got x1, x2, x3. How many constraints do we have? What's it do? Yeah, 3. So we're gonna have 3 slack variables. So S1, S2, S3, and then we'll have Z and then our numbers. So isn't that nice? You can go ahead and write down your whole matrix column headers right now. Now we're gonna go back and actually plug everything in. Now keep in mind, let's try it once. Can we go ahead and fill in all the information underneath slack and Z? Yeah, because it's going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And we also know that Z is always going to be equal to 0. So, just in terms of kind of cheating and doing a shortcut, we know that that's what it's going to look like underneath slack and Z. Furthermore, can we go ahead and fill in our totals? Yeah, we know our totals. Those are 30,000. 38,000, 48,000. And do we know what our coefficients are underneath x1, x2, x3? They gave them to us. They're just those. Those are the coefficients that go into the next part of the table. So we know it's going to be 2, 3, 2, 1, 2, 2, 2, 3, 1. And then what's the very last chunk? It's the objective function, but all the values are, it's not going to be 3, 6, 15. Negative 3, negative 6, negative 15. There. How did that feel? Did that feel better? We kind of, allowed ourselves to just go on autopilot and fill in the information rather than writing down each inequality and equation separately. Okay. So our goal is to make the whole bottom row positive. The method is to find a pivot. And we start with our 4 steps over there. Step 1, choose the most negative number in the bottom row. That's negative 15. Next, form all quotients in that column with the last column, right divided by left. So 30, I'm not going to write it out, I'm just going to write the answer. 30,000 divided by 2 is 15,000. 38,000 divided by 2 is 19,000. And 28,000 divided by 1 is 28,000. Those are my 3 quotients, and the smallest one is?
15,000.
15,000. So now I know my pivot column, my pivot row, this is my pivot number. Now you can see the fun you have in store for yourself. We need to cancel the 2 with a negative 2, cancel the 1 with a negative 1, and cancel the negative 15 with a positive 15. So to do the 1 and the 15, it'd be easiest if this were already a 1. But to take care of the 2, we could go ahead and just multiply the whole top row by negative 1. So I'm going to do that. I'm going to multiply the whole top row by negative 1. So negative 2, 3, negative 2, negative 1, 0, 0, 0, negative 30,000. And I'm going to go ahead and do my first pivot. So I'm going to keep, well, no, yeah, I'm going to change my second row now. So negative 2, that's negative 1, negative 1, 0, negative 1, 1, 0, 0, and 8,000. So that there is my second row. Did everyone else get that? Okay, might as well now multiply that whole top row by a half. Divide everything by 2, so I have my 1 in my pivot space. So divide by 2, 1, 1.5, 1, 0.5, 0. Okay, now we need to cancel out, using our pivot, we need to get rid of the 1, and we need to get rid of the negative 15. So now using my new first row here, I'm going to turn them all negative so that I can add it to that one. So negative 1, negative 1.5, negative 1, negative 0.5, 0, 0, 0, negative 15,000.
Okay, now this is where it gets visually very tricky. I'm going to add these blue numbers into my third row to create my new third row. This is enough to make you cry, right? A little bit. It's enough to just kind of, oh man, there's so many numbers to pay attention to. That's why you should use your hands to do it. So I'm creating a new third row by adding my blue numbers into my third row. So -1 plus 2 is 1. -1.5 plus 3 is 1.5. -1 plus 1 is 0. That's the 0 we wanted. -0.5 plus 0 is -0.5. 0 plus 0 is 0. 0 plus 1 is 1. And 0 plus 0 is 0. And -15,000 plus 28,000 is 13,000. Alrighty, we have that row. Now we need to get rid of -15. And we cancel the -15 with a +15. So I'm going to take this whole first row now and multiply it by 15. So times 15 times 15, that's 22.5. Times 15 times 15 times 15 times 15 times 15 times 15, 225,000. Okay, we're going to add those blue numbers into the last row. So 15 minus 3 is 12. And 22.5 minus 6, 16.5. And 15 plus -15 is the 0 that we wanted. 7.5 plus 0, 7.5. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. And 225,000. Did we do it? There's my pivot column that we wanted. Do I have another pivot column? Let's label everything. X1, X1, X2, X3, S1, S2, S3, Z, and a number. So that was one of our pivot columns. This was our other pivot column that appeared. And then we have our Z. Is the entire bottom row positive? Yes. All right, well then, that means, and we know X1, X2, and S1 are all 0. X1, X2, and S1 are all 0. And we know that X3 is equal to 15,000. And S2 is equal to 8,000. And Z is equal to 225,000. So what does this tell us to do? The manufacturing company wants to maximize profits. What is the maximum profit? $225,000. Going back to your page there, part C, or number 23, the answer is C, $225,000. Notice that we just did all that work to get information we already had. What are they telling us to manufacture? Product number 3. What's product number 3? C. Product C. And what did we know about product C from the get-go? It's the most profitable object there. So did this really take a rocket scientist to tell the company that they should make mostly product C? Maybe not. You know, maybe they're like, hey, you know, we kind of already knew that. But you're like, don't worry, now I know it for sure. Right? Because these constraints might have turned the tide. If these constraints, what if product C required 20 hours of assembly and 20 hours of painting and 10 hours of finishing? That could take up a lot of labor time. So much labor time that they're like, whoa, this isn't even worth it. Like, yeah, we're making a lot of profit from C, but look how much of our labor time it takes up just to make it. It's not worth it. So I hope you realize that just because C gives us the most profit, that doesn't automatically mean that we should just make the most of product C. That depends on what the constraints tell us. Okay, we're done with that one. So when you go home tonight, are you going to call all of your friends about the simplex method?
Yeah, I'm going to teach them it too.
You're like, hey, let me tell you about the initial simplex tableau and the simplex method. This is very exciting. And what'd you say, Don? You're actually going to sit down and teach them? Yep. That's wonderful. Don, that's one of the most hilarious things anyone has ever told me. Not only do I like it so Cross, cross, cross. Jill Sharp, we don't want to know you. Okay. Seriously, Dom, that's hilarious. I'm going to tell my family about that. My 2.5-year-old, when I go home, boy, so get this. She's going to really appreciate that too, the subtlety. All right. Folks, we're on our last idea. The last idea is really interesting, kind of cool, you know, just as cool as everything we've already been doing. So first, let's learn a new definition about a matrix. We've learned about the inverse of a matrix, which you need to use your calculator to find the inverse of a matrix. Now let's learn about the transpose of a matrix. Transpose. Transposition. Do we ever use the word transpose? No. Do we ever use the word transposition? No. So there's a brand new word for us just for matrices, and the transpose means this. Rows become columns. So we're basically going to turn the matrix 90 degrees such that each row becomes a column. So let's go ahead and call this matrix A. That's matrix A. Now let's write down A transpose. So we're going to find the transpose of this matrix. To be very helpful to say it out loud, and what you're going to say is take your row 0, 2, 4 and make it a column. 0, 2, 4. Take your next row 2, 1, 3, make it a column. 2, 1, 3. Take your next row 9, 8, 7, make it a column. 9, 8, 7. Anyone have a better word for this than transpose? Flippy floppy? Yeah, I don't know. Okay, next one. Now notice, when you did the transpose, this was a 3x3 matrix, still a 3x3 matrix. When you turn the rows into columns, what do you think happens to the dimension, the size? This is a 2x4. What do you think the result is going to be? 4x2. It'll become a 4x2. So when you do a transpose, you actually switch the rows and the columns, literally. So you're switching the dimension as well. So we already know ahead of time that this is going to become a 4x2. So draw your matrix accordingly. We want 4 rows and only 2 columns. So you'll notice this was a wide rectangle. Now it's a tall rectangle. So again, make your row a column. The row 6, 8, 1, 2 becomes a column. 6, 8, 1, 2. The row 1, 7, 8, 6 becomes a column. 1, 7, 8, 6. Oh, and we should label that. That's matrix A. This is matrix A transpose. Is that it? Yeah, that's it. That's the whole last method, folks. No. But that is a key idea that we need, is to do a transpose. Now, fortunately, just so you know, Don, that is it in terms of the additional information we're going to learn in order to do this last method. The last method is still just the simplex algorithm that we already learned, but we do have to do this. Okay. Next page? Or is it on the bottom of that page? All right, so we're going to take a look. Now, it so happens that the simplex method that we've already learned is only for maximization problems. Okay, so every problem we just did, I could have said this earlier, it's always for maximizing a situation. Okay? Do you think they want to come in and learn this one?
Yeah.
Yeah.
Do we need a door unlocked?
No, I mean, we're already in here.
Oh, that's what I thought. But I'm like, okay.
You mean to my heart? Oh, he didn't even care. All right. Okay. So, all the problems we already did were maximization problems. So if you turn one more page, you'll see that we're going to get to minimization problems. And the whole idea is we cannot use the simplex algorithm that we just learned on a minimization problem because it's just, they're built for different things. The simplex method was for maximizing. So what on earth do we do if we have a minimizing problem? We transpose the matrix, and it turns it from a minimizing to a maximizing problem. So to be fair, you see these two problems, number 27 and 28? Let's just ignore those for a second because those are already maximization problems.
which we could use the simplex algorithm to solve. So let's look at 29. What we have here is a minimization problem. And you'll notice now that we're using the y variables. We're using y1, y2. So what are we talking about here? We have a couple of products. You know, the products could be anything. They could be a product, or it could be an airplane 1, airplane 2. It could be a... You need to do at least 19.5 or above, and at least 24 or above. But then you want this constraint here to be minimized. So what are we really talking about? Probably cost, right? This is the cost of those objects. And then this is the overall cost to your company. And you want to minimize cost to your company. So here's what we do. We're going to create a teeny tiny little matrix. We're going to call it matrix A, first of all. And what goes into that matrix is the information exactly as you see it. So your first constraint, you get to just put 1, 1, 19.5. The second constraint, 2, 1, and 24. And then you get to get the coefficients from your objective function and put them in normal, not negative, 5, 2, and the last number is always a 0. But folks, trust me. As I tell you this, I think to myself, what must they think? This sounds like magic. Why would this work? Why does this mean anything? We're just putting numbers into a matrix. Why does any of this turn into a meaningful problem? And those are good questions. Right now, we're going to focus on the method. All right, so we have this minimization problem. We put the information in, and then we find the transpose matrix. By doing the transpose matrix, let's focus here. This was a minimum problem using variables, this was a minimum problem using variables y1 and y2. By doing the transpose matrix, we are now looking at a maximization problem using variables x1 and x2, like we always have been. So let's go ahead and turn our rows into columns. So the first row, 1, 1, 19.5, 1, 1, 19.5. Our second row, 2, 1, 24, becomes the column 2, 1, 24. And our last row, 5, 2, 0, becomes the last column, 5, 2, 0. So we took the information from the minimization problem and turned it into the information for the maximization problem. Now let's extract that information right out. Let's extract it right out. This is actually 1x1 plus 2x2, which has to be less than or equal to 5, and 1x1 plus 1x2, which has to be less than or equal to 2. And our z function, our maximization of profit, whatever, is 19.5 x1 plus 24 x2. And now this is a problem that you can solve with simplex algorithm, which is that whole algorithm that we just did. Okay, there's something more to say here. If we were able to find the solution to this problem, for instance, graphically, right? We could always solve any problem graphically. I can just take my constraints, I can turn it into a graph. I'd have one line here, another line here, I'd find my corner points. I'd plug in all the corner points, and I want to minimize that, so I find the corner point that has the smallest value for W, right? And that corner point, whatever it is, that corner point that gave me the smallest value for W, that exact same corner point, so whatever that value was, like let's say that those were the values y1 equals 8 and y2 equals 3, for instance. That minimum value for this system, didn't even matter that that was 8 and 3, I take it back. that minimum value for this system is going to be equal to, now I come over here, I do this whole thing, I find my corner points. That's going to be equal to the maximum value over there. So, I mean, first of all, let's notice these are different inequalities. These inequalities have to be greater than 19.5 and 24. These inequalities have to be less than 5 or less than 2. The key is that whatever the minimum value of this objective function was, it's going to be equal to the maximum value of this objective function. Again, I realize that just sounds like pure magic. Right? We're saying that if you have a system that you want to minimize over here, and if you could find the answer, then by transposing this matrix and turning it into a maximization problem, you can solve that with the simplex algorithm. The minimum value over here is okay. Okay. That's what we're saying. So what do we really want to do now? We want to still solve this original problem, the minimization problem, but the simplex algorithm only works for maximization problems. So now what we have to do is come over here, do the whole solution, and then once we're done maximizing z, that will be equal to the minimum value of w. So let's do it. Let's solve this problem. Let's solve it. What do we have here? We have 2 constraints, so 2 slack variables. So let's make our matrix. Here's our matrix. It's going to be x1, x2. We have 2 constraints, so 2 slack variables, s1, s2, z, and the numbers. And so our first inequality is 1, 2. We're going to use the slack variable, but not that one or that one. And that's equal 5. Our second constraint is 1, 1. We're not using the first slack variable. We are using the second slack variable. We're not using z, and that's equal to 2. And then our our objective function, remember we just moved both of those terms to the left. They both become negative. So now negative 19.5, negative 24, 0, 0, 1, 0. Okay, again, big picture. We want to actually solve the minimum value of this problem. But the simplex algorithm doesn't find minimums. So we take the transpose of this information, and that turns it into a maximization problem. Now we're just going to go about our business solving the simplex algorithm. So let's go ahead and do it. First of all, step 1, what's the most negative indicator, or what's the most negative value? Negative 24. Now form all of our quotients. So our quotients would be right divided by left. 5 divided by 2 is 2.5. And 2 divided by 1 is 2. So the smallest quotient is 2. So this will be our pivot. That was very convenient. That's already a 1. So let's go ahead and pivot. Let's cancel the 2. In order to cancel the 2, we need a negative 2. So we're going to multiply that whole row by negative 2. That'll be 2, 2, 0, 2, 0, negative 4. So we're going to add that into the top row. So that'll be negative 1, 0, 1, 2, 0, 1. We get to keep the middle row because it already has a 1 there. So 1, 1, 2. And now we want to cancel out a negative 24 in the bottom row. So we multiply the entire middle row by positive 24. So times 24, times 24, times 24, times 24, times 24, times 24. That gives us, we're going to add the middle row into the bottom row. So that's 4.5. That's 0. That's 0. That's 24. That's 1. And that's 48. Oh my gosh. Folks, you're not even going to believe what's about to happen. You're not even going to believe it. So first of all, are we done solving that problem? Yeah, the entire bottom row is positive. So let's finish our solution to this problem. So I'm going to label all my columns. This was x1, x2, slack 1, slack 2, z, and a number. And so the columns of interest are x2 and slack 1, and z equals 48. So first of all, let's just say what we know about the maximization problem. The maximum value of z, so the max z is 48, right? Here's magic number 1. That now tells us that the minimum value of w over here is also 48. So the minimum w is 48. So that's what this whole setup just did for us. This whole use of a transpose, just so everybody knows. So first of all, this whole thing was called the simplex algorithm. What we just did by using, turning this information into the transpose, this whole idea right now that I'm allowed to say that the maximum value of z is equal to the minimum value of w, this whole thing. Some of you are saying, it really is the end of the world. Okay, so duality theory tells us that if you know something about this minimization problem, you know something about this maximization problem. And if you know something about this maximization problem, you know something about this minimization problem. That's duality theory. Dual means, pair. And so the first thing we found out is that the maximum value in z is 48, therefore the minimum value of w is 48. However, there's still one more thing we want to find. We want to find what actual values of y1 and y2 lead to that. We have no idea right now. Let's finish this problem. We now know that over here, x2, well, first of all, we know x1, s2 are both 0. So if x1 equals s1 equals 0, then we know x2 is equal to 2, and slack 1 is equal to 1. So that's just this problem, That's how we maximize the z objective function over here. However, is everybody ready for this? Is everybody ready for this? Are you ready? I mean, really, are you ready? The value of the slack variables in the bottom row, so that's the slack 1, slack 2. The value of the slack variables in the bottom row, anyone want to guess? Anyone want to guess?
That's the answer.
That is the value of y1 and y2 that minimizes w. What? That's redonkulous. Okay, so now the minimum value of w is 48, where y1 is equal to 0 and y2 is equal to 24. That's duality theory. Duality theory is you take the minimization problem, you turn it into the transpose matrix, you make it a maximization problem, you solve the whole thing using the simplex algorithm, and whatever the maximum value of z is, that's the minimum value of w, and whatever the values of the slack variables are in the bottom row, that is the value of y1 and y2 that will minimize this system. Now everybody check. Hold on, check. What if I plug in 0 for y1 and 24 for y2? If I plug in a 0 right here, and I plug in 24 right here, does that indeed equal 48? Oh, snap. Okay, folks. I feel like, by watching you all, I feel like I just abused you for the last 2.5 hours. I feel like you're telling me, Mr. G, you just abused us for the last 2.5 hours. But here's the great news. Great news. We finished. Which means, if we look at the schedule, we still have all next class period to do chapter 5, and we have. Wait, do we not have a catch-up day? Is that the right schedule? I thought I always gave us a.
No, you had the what test on? Yeah, you had the test for Valentine's Day. That's it.
There we go. Yeah, take a look. Next week we can do all on next class period. So this Thursday we can do our finance, and then we have a whole catch-up and review day.
to just do this.
Well, yeah, which means that we have a whole extra class period built into this to review and be ready for the test, which means we have a whole class session that we could do the practice test together. Not just some of the problems, but all of the problems. So I realized that that was a lot to take in today, and your brain might hurt a little bit. But just, go home tonight and go to sleep. I hope you go to sleep. And then when you come back, we're going to finish the rest of these, right? We still have to finish the rest of these duality problems. We only did one of them. We still have more to do. So when you come back on Thursday, we'll finish this, and then finance, and then we'll have a catch-up day. And I bet you all want your test.
Miss Cheryl.